this is a quick overview of some of the questions we went over in class, Math 154, after Exam 1, before Exam 2, in fall of 2016. And my students, there's notes online about this. Most of the material, like most of the exercises we did in class were just from the textbook, but we made up these couple examples, so I just wanted to talk about this. So the first concept I want to talk about is critical path, okay, in relation to this particular digraph. Okay, so what is a critical path for the above digraph? And you're supposed to, at this stage, find it just by trial and error. One thing you should think about is if you have a vertical line, right, vertical line, and you just take it like this, and you just move it around. As you move it around, it's going to cut the critical path exactly once at every moment. Wherever that critical path ends up, this vertical line will cut it exactly once at every moment. Okay? So keep that in mind. So you have various possibilities. You could have the critical path be like this. You don't have to consider the start and the end because those are free. So that might be the critical path. Or this one might be the critical path. Or maybe this is the critical path. So you have to figure that out. So in some cases, so for example, if I just draw this line, say here, I can be pretty sure that either the critical path goes through T3 or through T9. In this case, it can't go through both because it has to choose. Although there may be two critical paths of the same length, and then you could choose. It's the length of the critical path is unique to every digraph. It's the length, not specifically the path, because you might have more than one critical path that are the same identical length. That's okay. Okay. So if I'm going to think in terms of, here's my guess, I'm going to guess this path, this one, I'm going to guess this, and then I'm going to say, wait a minute, let's see, it's definitely, I can't improve upon this, I'm going to add this up, 5, 8, plus 4 is 12, 15, 19, 23, okay, that's 23. And I'm going to try to make it longer by wiggling around. If I include T9 and don't include T3, will that help matters? Will that make the critical path longer, or my suspected critical path? No. So T3 is heavier than T9. The weight on T3 is heavier than the weight on T9. So there's no point in diverting through T9 unless I can grab other things with it, and so it doesn't make sense. Let's see. So if I go about 5, 3, 5, 4, that looks kind of heavy. If I go 5, 3, 5, 4, is that going to be of any use? Well, that's going to be 17. That's not very good. Well, what if I do something like this? That's 11 plus 8, which is 19, so it's clear that going around that way is more expensive than this one. That's true. What else? Okay, so after messing around with it, you should conclude that this is the critical path, and as we're staring at it, let's double check. Am I lying to you? So for example, to go from T7 to T4, actually I am lying to you. So because I could go around this way and it would take up more weight. So let's see how I can fix that error. I shouldn't have made this squiggly so much. There we go. So let's try this. That's 10 plus 10 plus 8 plus 3. 1. Can I make that worse somehow? I don't think so. Yeah, I think I got it. And the question is whether my answer key is wrong. Let me pause the video. Ah, my answer key is right, but the video is wrong. Yay! That's why we paused the video. So you probably saw this. This is the better one. Yay. It's easier to think when you're not recording. Okay, so that's actually the critical path. And that is 23. And the point is, now I'm going to be scheduling my machines heuristically. I'm not going to be using any rules other than my intuition and guessing and checking until I can't make any more changes, and I've tried everything. So we're going to be using a different technique for some of the exercises in the book. But for this exercise, you're supposed to be just doing it as an experiment. Now, the question is whether all these other tasks down below can be squeezed into a second processor. Clearly you need a processor for the critical path, so this guy is going to get its own machine. Okay? When you're just trying to figure out how to optimize this off the cuff. Okay, and then I'm going to try to see if I can squeeze the rest of this into a second machine, thereby demonstrating that 2 machines should be sufficient. Okay, so let's try that. I guess, there we go. Okay, so I'm saying to verify a suspected critical path, do what we just did and mess around with it until you're convinced that that's the best critical path. Again, I'm not being mathematical here because there are algorithms and we can talk about that, but right now I just want you to figure it out by your gut. Okay, so the critical path costs 23 and the rest of the digraph costs 16, and so the guess is, can we, and here we do it, just line up T1, T2, T3, T4, T5, T6. We just happen to label those in the right order. The critical path is T1, T2, T3, T4, T5, T6. So I'm putting the critical path here. Okay, there's the critical path. And let's see if the rest of the tasks can fit in. So how did the rest of these tasks fit in? Let's figure out how this occurs. So T7 is available to start immediately because it doesn't have any prerequisites. And you may say, well, what about this? Well, that doesn't really exist. That's just there so you can get a sense for the flow of how things work around here. So that start task and the end task are phony. That's why they're in red. They don't really exist. Okay, so they're gone. Now we're going to see about scheduling this guy. So T7 is scheduled over here. All right. And then what about T8? T8 only has to wait for T7, so we can start that guy immediately. But then why do we wait? We wait because T9 has to wait on T2. Okay? So these two chains don't, not really a chain, what do you call it? This other path through here, which is not a critical path, but an interesting path. This interesting path does depend on T2. So we have to wait for T2 to finish. That's why we put a little X there to indicate that we are waiting, and then T9 can start right away as soon as T2 is finished. So we're good. Okay. And then after that, T10 is happy as soon as T9 is done, and T11 is happy as soon as T10 is done. Okay, so T6 has to theoretically wait for T10, but you see it's happening so early it doesn't really matter. That dependency doesn't end up costing us anything. Okay. Notice we are not using the list processing algorithm at this point. We will, but we aren't right now. Next graph, we have a similar line of questioning, and for the critical path, notice, for example, I just made this miniature copy of this. You don't have to look at that if you don't want to. Okay, so I just made a line here, and in this case, either T9 is involved or this edge. If this edge is involved, then both T10 and T11 have to be somewhere on the critical path. So that's something to think about. So you can think about all the options that go through T9 including T10, it doesn't matter, but all the options that go through T9, and separately consider all the options that go through T10 and T11. So if it goes through T10 and T11, then there's really only two options. You can either go around that way or that way. So clearly, if we're going through T10 and 11, then that's what the critical path looks like. All right, so that's one option. Okay, but the other option would be to do something like this. That's an option. So this is an option, or even this is an option, and that ends up being the one we're going to go with, because we try most everything is a 10, but this guy costs 11, and once you hit upon it, you're like, oh, okay, that's got to be the right critical path, because any additional swap outs I can think to do don't make it any longer. So the critical path, you can say CP if you want to abbreviate, has a weight of 11. Okay. Then we go ahead and try to schedule this dude down here, and so what's happening is we've got, I'm just getting tired of seeing those lines. Okay, so if I try to schedule this, if I dump the critical path right there, like we've been doing, then T1 is already free to start, so I may as well start T1 on machine 2. The problem comes, that's why I've made T8 in red, that both T8 and T2 can make a claim that they need to be in this spot because T9 cannot start until both of them are finished. Okay, so both of them have the claim, and so there's a problem because we have some kind of collision here. T1 is not a problem because nobody else can start, so T1 may as well go ahead and start. But then T8 and T2 have to be squeezed in here somehow. So if we have 3 processors, we're good to go, and the rest of this isn't a problem. As you'll see down below, like you can schedule it. I don't think I scheduled it on 3 processors, but anyway, I don't think it's a problem. You can go ahead and try. I said possibly more because you can't just say, hey, 2 is enough. You can say, hey, 2 is probably enough. And if you don't actually try it, you can't be absolutely sure that one of these dependencies, maybe that edge or something, is going to get in the way, possibly. So you'd have to go ahead and try the whole thing to see if it works, but it probably works. Okay, but now we can say something else. We can say, hey, you see, notice that this T2 isn't very heavy, so we may as well go ahead and split this guy. I'm going to cut it right here, and I'm going to split it apart, okay, into, so here's where I split it, okay. And then I just was able to squeeze all the other tasks in, and it wasn't a problem. So we're really only wasting 1 time unit. Each processor is only waiting 1 time unit. It seems fairly efficient to me. And that's all I really wanted to say about those graphs. The homework that's going to be assigned is on page 111 of the book, and hopefully this helps somebody who would have been absent. If you have more questions, definitely read the book. The whole point of giving you the book is so that you can read it, and so you've got a video and some notes, and if you're still confused, come see me.